Before we jump into the thick of things, let's first differentiate the terms oscillatory motion and periodic motion. As seen in the definitions, oscillatory motion is a special case of periodic motion where rigid bodies are involved. With that out of the way, let us imagine a conservative system with a rigid block attached to an ideal spring. We stretch the spring a particular displacement, x1, to the right of the equilibrium position, x0, in order to store elastic potential energy inside the spring. We then release the block so that the restoring force, F sub r, applied by the spring pulls and pushes it past x0 repeatedly. This sort of repetitive motion will continue to go on indefinitely until an outside force stops it. In this idealized case, we can describe the motion of the block by utilizing the equations of simple harmonic oscillation. Looking at the diagram, we can see that simple harmonic oscillation is just the tip of the iceberg. However, studying this idealized case is the stepping stone in understanding other more challenging cases. This leads me to teaching strategy number 1. Define clearly what type of oscillation is being considered. This helps the students in understanding what parameters are involved, so you may proceed with the calculation part smoothly. Now, going back to the spring block system, if the restoring force is directly proportional to the negative of the displacement, we have the following where we apply Newton's second law in order to arrive at a second-order differential equation, which has possible solutions as follows. Don't worry, the full derivation will be given out as free material for you to use. Now notice that we have chosen omega to be equal to the square root of k over m. As to the question of why, just put it in the corner of your head as we will use it later. Relating all of this to rotational motion, we can imagine a particle moving under uniform circular motion as shown. From the figure, we see that the x component of the radius becomes a cosine theta. Recall also from rotational motion that the centripetal acceleration, a rad, is equal to negative omega squared r, where in this case, r is equal to a, and the negative sign indicates that the direction is towards the center. The x component of a rad, denoted by a rad x, is equal to a rad cosine theta, and eventually becomes negative omega squared a cosine theta. We substitute x for a cosine theta, which will lead us to a second-order differential equation with the same, and in fact equal solution to the spring system a while back. This proves that the previous substitution we made for omega holds water. This also suggests that we may use other equations in uniform circular motion, like the equation of the period and that of the frequency. This leads me to teaching strategy number 2. Relate simple harmonic oscillation to uniform circular motion. This not only serves as an avenue for other useful relationships to appear, but it also checks the comprehension on the topic of rotational motion. Two birds with one derivation per se.